Dear students, now we are going to discuss transverse magnetic waves between parallel planes. Transverse magnetic waves are also known as TEM waves. Let's start with the definition of transverse magnetic waves. So here in this transverse magnetic waves, there is no magnetic field intensity in the direction of propagation. That is, the magnetic field intensity is entirely transverse in the direction of propagation. Here we can consider the wave is propagating in the z direction. Then the magnetic field intensity in this direction becomes 0. You will understand this one, but it has the magnetic field intensity in the other directions like y, but not in the direction of propagation. So that is the condition for transverse magnetic waves. At the same time, it has that electric field intensity in the direction of propagation. So here Hz is equal to 0, but Ez is not equal to 0. Hence it is also known as E wave. You will understand the concept of transverse magnetic waves. So here the magnetic field strength is entirely transverse in the direction of propagation. Okay, so next we are going to derive the field components of this TEM waves. So here we can consider the general field components of an incident wave along the parallel plane. So we have already derived the field components of incident wave along the parallel plane. So you have to remember all these four general field components. So here Ex is equal to minus gamma by h squared dou Ez by dou x. Ey is equal to j omega mu by h squared dou hz by dou x. Hx is equal to minus gamma by h squared dou hz by dou x. Hy is equal to minus j omega epsilon by h squared dou Ez by dou x. So you have to remember all this general field components of the wave along the parallel plane. Okay. So next we are going to derive the field components for this TEM waves. So for TEM waves, Hz value is equal to 0. Then this term becomes 0 and here this term becomes 0. Do you all understand this one? So for TEM waves, Hz is equal to 0. Then the general field components Hx, Ey also 0. So here we can get Hx, Ey and Hz. These three components are equal to 0. We can have Ex is equal to minus gamma by h squared dou Ez by dou x, and then Hy is equal to minus j omega epsilon by h squared dou Ez by dou x, and then Ez is not equal to 0. So here we can consider this is the first one and this one is the second equation, and we are going to find out the field components Ex, Hy and Ez. Do you all understand this concept? Next we are going to find out the field components of this TEM waves. So for that we can take the general wave equation. The general wave equation for magnetic field is del squared H is equal to gamma squared H. So in this one we can consider the parallel planes with the distance A. So it starts from minus a by 2 to plus a by 2. The total distance is A. Here we can consider Hz is equal to 0. It has Ez value, Hy value and Ex value. So these three are the field components for this TEM waves. Okay. So here we are going to analyze the wave equation to derive the field components of this TEM waves. Okay. So here the wave equation is del squared H is equal to gamma squared H, where del squared is the Laplacian operator dou squared by dou x squared plus dou squared by dou y squared plus dou squared by dou z squared. So we are going to replace this del squared with this value dou squared h by dou x squared plus dou squared h by dou y squared plus dou squared h by dou z squared is equal to gamma squared h. So in this TM wave, we are having only the term Hy. Here Hz is equal to 0, Hx is equal to 0. So we can have only Hy component. So we are going to replace all this H with the value Hy. So here we can take dou squared Hy by dou x squared plus dou squared Hy by dou y squared. So in that particular direction, that magnetic field strength is 0. So in the direction of, if the wave is propagating in the direction, then the Hy component becomes 0. Correct. So here we can say dou Hy by dou y is equal to 0. You all understand this one? So this is very important. If the magnetic field is propagating in this particular direction, then its differentiated value becomes 0. So here we can remove that value dou squared Hy by dou y squared. So next we can have dou squared Hy by dou z squared is equal to gamma is the propagation constant. So gamma squared value is minus omega squared mu epsilon. So we can replace this gamma value with this minus omega squared mu epsilon. This H becomes Hy. So here we are going to consider the Hy value as H naught e power minus gamma z. So any magnetic field or electric field can be represented with its magnitude along with its phase. H naught is the magnitude, e power minus gamma z is the phase component. So in this equation, we are going to differentiate with respect to z because the wave is propagating in the z direction. So we can simply replace the z component alone, not this x. Okay. So dou squared Hy by dou x squared plus dou squared by dou z squared. This Hy can be written as H naught e power minus gamma z. You will understand this one. Then we are going to differentiate this term with respect to z. So if we are going to differentiate this term means, as we know that dou by dou z of e power minus gamma z is equal to what? Minus gamma e power minus gamma z. If we are going to differentiate again this term, we can get minus gamma into minus gamma e power minus gamma z. That is gamma squared e power minus gamma z. So dou squared by dou z squared of e power minus gamma z is nothing but gamma squared e power minus gamma z. So we can replace this term with gamma squared H naught e power minus gamma z. For further simplification, we can move this term to this side as plus. Then we can get dou squared Hy by dou x squared plus gamma squared. So again we can replace this value as Hy. Correct? Hy is equal to H naught into e power minus gamma z. So we can replace this value as Hy, and here we can take plus omega squared mu epsilon. Hy is equal to 0. So in this one we can take this Hy as a common. Then we can get gamma squared plus omega squared mu epsilon into Hy. For further simplification, we can consider this term as H squared. So this H squared value is very important to analyze the characteristics of the wave nature. Okay. So here we can write this equation as dou squared Hy by dou x squared plus H squared Hy. So this term becomes H squared. So what is H squared? That is equal to gamma squared plus omega squared mu epsilon. So this value is very important. So from this we can find out the characteristics of TM waves. Okay. So here this is the general wave equation for this TM waves. So it is the second order differential equation. So we are going to solve the second order differential equation. Then we can get the constant value sin Hx plus the constant value cos Hx as a solution. Okay. Then we can get the solution of the second order equation as Hy is equal to C3 sin Hx plus C4 cos Hx. So actually the C3 and C4 are the arbitrary constants. So for TE waves, we have used C1 and C2. So for TM waves, we can use C3 and C4. So consider this as the third equation. So this is the general solution of the second order equation. If the magnetic field is expressed in both time and direction, we can include the propagation constant gamma in this one. So the same solution can be written as C3 sin hx plus C4 cos hx e power minus gamma z. So here we can include both time and direction. So consider this as the fourth equation. This is very important equation. From this we can find out the field components. So here we are not going to use the boundary conditions to find out the values of C3 and C4 because for this tangential component of magnetic field is not continuous. So we cannot apply this boundary conditions for magnetic field because this HT value is not equal to 0. That means it is not continuous one. So boundary conditions cannot be applied. Okay. So for that we are going to find out Ez value. Then we are going to apply the boundary conditions in electric field and then find out the field components. So for that we are going to find out the Ez component first. So here we can take the second equation. What is the second equation? That is the general field component Hy is equal to minus j omega epsilon h squared dou Ez by dou x. So we are going to find out the Ez value. So we are going to keep this one and move this value to the other side as a reciprocal. Then we can get dou Ez by dou x is equal to minus h squared by j omega epsilon into hy. Okay, then we are going to integrate on both the sides with respect to dx. Okay, so here we are going to integrate both the sides. Then we can get integration of dou Ez by dou x with respect to dx. We can get Ez. So similarly in the right hand side we can get the integration of minus h squared by j omega epsilon hy with respect to x. Okay. So in this one we are going to substitute the fourth equation. So what is the fourth equation? The general solution of hy. Okay. So next we are going to substitute that hy expression here. Then we can get Ez is equal to minus h squared by j omega epsilon integration of C3 sin hx plus C4 cos hx e power minus gamma z dx. Do you all understand this one? So here we are going to simply substitute this hy value, that is the fourth equation. Okay. Then we can get Ez is equal to minus h squared by j omega epsilon into integration of sinus minus cos. So minus C3 cos hx by h plus integration of cos is sin. So C4 sin hx by h e power minus gamma z. The next step we can simplify this term and then multiply this minus j omega epsilon inside this bracket. Okay. Then we can get Ez value as plus h by j omega epsilon C3 cos hx minus h by j omega epsilon C4 sin hx e power minus gamma z. So this is very important equation. Consider this as the fifth equation. Because we are going to apply boundary condition for this Ez term to find out the C3 and C4 values. Okay, as I told you, boundary conditions cannot be applied directly to magnetic field component. So we can apply this boundary conditions only for electric field component. There are two boundary conditions. One is Ez value is 0 at x is equal to 0. Ez value is equal to 0 at x is equal to a. That means, as I told you, the parallel planes, the distance is a. So we can consider x is equal to 0 to x is equal to a. That means on the surface area, the Ez value is equal to 0. That is the boundary condition over here. So now we are going to apply the first boundary condition Ez is equal to 0 at x is equal to 0 in this fifth equation. So this fifth equation is very important one to find out the arbitrary constants to proceed further. Okay. So here we are going to substitute this value in the fifth equation. So Ez value becomes 0 when x is equal to 0. So here 0 is equal to h by j omega epsilon C3 cos hx. Correct? Cos hx, x value is 0. Then its value is cos 0. So what is that value? 1. Minus h by j omega epsilon C4 sin hx. Here x is 0. Then we can get sin 0. Its value is 0. Okay. So it can be represented as C3 h by j omega epsilon e power minus gamma z is common. So we can take this value is equal to 0. So we can move all the terms to this side to find out the C3. So we are going to move this to this side. That means 0 multiplied with j omega epsilon by h into e power minus gamma z. So all the terms becomes 0. Correct. So C3 is equal to 0. So next we are going to apply the second boundary condition. Ez is equal to 0 at x is equal to a and also C3 is equal to 0 in fifth equation. So here we can write Ez value is equal to 0 when the C3 term is 0. That is the first term becomes 0. The next term is minus h by j omega epsilon C4 sin hx. X is nothing but a is equal to 0. Do you all understand this one? The same fifth equation we are going to substitute C3 value as 0. X is equal to a. So then we can get Ez is equal to 0. Okay. Then we can move this minus h by j omega epsilon to this side. Then the term becomes 0 again. Then we are going to move the C4 this side. 0 by C4 is equal to again 0. Then we are going to find out the HA value by moving this sign to this side. So here we can get sine inverse of 0. So whenever we can get the 0 value for sine m pi. That means sine 0 is 0, sine pi is 0, sine 2 pi, sine 3 pi, sine 4 pi. All the pi values are 0. Do you all understand this one? So here we can say HA is equal to sine inverse of 0. That value is nothing but m into pi. Here m is nothing but 0, 1, 2, 3 up to infinite. So from this we can get the value of h. H is equal to what now? M pi by a. So this is very important. So now we have obtained C3 is equal to 0, h is equal to m by a. So now we are going to substitute these two values in the fifth equation to get Ez value. Do you all understand this one? Now we are going to substitute C3 is equal to 0, h is equal to m by a in this fifth equation to get Ez value. So Ez is equal to 0 minus h by j omega epsilon C4 sin hx e power minus gamma z. Because here C3 term becomes 0 and next we are going to substitute h is equal to m by a. Then the Ez field component is equal to minus C4 by j omega epsilon h is equal to m by a sin h value is m by ax e power minus gamma z. So this is the Ez field component for TM waves. Okay. So next we are going to find out hy value. So for that we can consider the fourth equation. So what is the fourth equation? That is the general solution of the second order equation. So hy is equal to C3 sin hx plus C4 cos hx e power minus gamma z. So in this one we are going to substitute the C3 is equal to 0 and h is equal to m by a. Okay, then we can get C3 is 0, h value as m by a. We can get the hy component for TM waves as C4 cos of m by a x e power minus gamma z. So consider this as the seventh equation. So this is another field component of TM waves. Okay. And finally we are going to derive the Ex field component for TM waves. Okay. So here we can consider the first equation. So what is the first equation? That is the general field component Ex is equal to minus gamma by h squared dou Ez by dou x. So here we are going to substitute the sixth equation, that is the Ez value, that is sixth equation in this one. So we can get minus gamma by h squared can be replaced with m by a the whole square dou by dou x of what is the sixth equation? Ez value, that is minus C4 by j omega epsilon m by a sin m by a x e power minus gamma z. Okay, so we are going to differentiate with respect to what? X. So we are going to keep this value alone inside the bracket and move all other terms outside this. We can get minus into minus plus gamma by m by a the whole square C4 by j omega epsilon m by a e power minus gamma z. So dou by dou x of sin m by a x. So here we can simplify this term. Then we are going to differentiate the sign with respect to x. So differentiation of sin is plus cos. So we can get cos m by a x. Here we can have m by a along with this x. So we are going to take this term. So here differentiation of sin m by a x is nothing but cos m by a x into m by a. Then we can simplify this term further to get the Ex value. Do you all understand this concept? Then the Ex value can be obtained as gamma by j omega epsilon C4 cos m by ax e power minus gamma x. Consider this as the eighth equation. And so this is the Ex component of TM waves. So we have obtained all the field components of TM waves between parallel planes. So from the equations 6, 7 and 8, we can list out the field components as Ex, Hy and Ez. Okay, so these three are the field components of TM waves between parallel planes. Okay, so for further simplification, you can consider the propagation constant. So propagation constant gamma is equal to alpha plus j beta. So alpha means attenuation constant, beta means phase shift constant. So here, if the wave propagates without any attenuation, that means alpha is equal to 0, then the propagation constant can be written as j beta. It is having only the phase change, that is phase shift constant. Then the same 6, 7 and 8 equations as Ex is equal to beta by omega epsilon, because we are going to replace this gamma as j beta, then j divided. Then we can get beta by omega epsilon C4 cos m by ax e power minus j beta z. So in this term we don't have any gamma outside. So here we can get Hy is equal to C4 cos m by ax e power minus j beta z. So in this Ez, we are going to replace this gamma as j beta. Do you all understand the concept? Then the field components for this TM waves between parallel planes are represented as Ex is equal to beta by omega epsilon C4 cos m by ax e power minus j beta z. Hy is equal to C4 cos m by ax e power minus j beta z. Ez is equal to minus C4 by j omega epsilon m by a sin m by ax e power minus j beta x. So these are the field components for TM waves. Okay. So here we can take TM10 wave. So for this TM10 wave, the electric field can be represented like this between the parallel planes, and here we can have the magnetic fields like this. Okay.